Let's talk about the concept of linear dependencies and the model of flatness in different dimensions. So let's try to visualize them. So first, we have one-dimensional straight line in two-dimensional space. So this is the simplest form of linear dependencies in two-dimensional space, like a graph paper. And a one-dimensional straight line can be represented by the equation y equal to mx plus c, where m is the slope and c is the y-intercept. So this line represents all of the points of xy that satisfy this equation. Here we have a two-dimensional flat surface in three-dimensional space. So visualizing a plane requires us a three-dimensional graph where the plane cuts through the 3D space. So the plane can be represented by the equation ax plus by plus cz plus d equals 0. Here, ABC are coefficients that determine the orientation of this plane in this three-dimensional space, and d is a constant. So any point xyz that lies on this plane satisfies this equation. Let's talk about hyperplane in higher dimensions. This is more abstract and cannot be directly visualized beyond 3 dimensions, but the concept remains the same. It represents a linear equation in higher dimensions. So higher dimensional hyperplanes extended the concept to more than 3 dimensions. A hyperplane is an n-dimensional space which is defined similarly by a linear equation but with more variables. A sub 1 times x sub 1 plus a sub 2 times x sub 2 plus ellipsis plus a sub n times x sub n plus d equals 0. So this hyperplane is a subspace of dimensional n-1 in n-dimensional space. So for higher dimensional hyperplanes in 4 or more dimensions, visualization sometimes becomes challenging due to the limitation of 3-dimensional space that we can perceive. However, this concept is the same with the hyperplane being n-1 dimensional flat surface in n-dimensional space, which satisfies a linear equation involving n variables. This graph is a straight line which is defined by the equation y equals 2x plus 1. So this line is a one-dimensional structure in a two-dimensional space where each point on the line satisfies the linear equation. Let's talk about nonlinear curve in two-dimensional space. So here is an example of a quadratic function, such as y equals x squared. So this function produces a parabolic curve, which is clearly burns as it moves around from the origin. So this curve clearly burns upwards as x increases from 0 or x decreases from 0, which illustrating the nonlinear nature of the function. Unlike the straight line, this function changes its slope at every point, right? Which is a key characteristic of the nonlinear behavior. Here is a 3-dimensional plot showing a plane defined by its equation z equals negative 0.5x minus 0.3y plus 5. So this plane extends infinitely in x, y, z direction, but it remains flat. So every point x, y, z on this plane satisfies this equation, which making it a two-dimensional flat surface in 3-dimensional space. Let's consider a nonlinear surface in 3 dimensions. We'll consider something like a saddle surface, which is represented by an equation z equals x squared minus y squared. So this surface bends upward to one direction, right, and downwards in the opposite, which creating a saddle shape, which is clearly nonlinear. This surface exhibits upward curvature along the x-axis and downward curvature along the y-axis. Such complexity in the surface curvature distinctly mark it as a nonlinear, as it doesn't maintain any consistent flatness, but it bends in multiple directions.